by P. So these were some examples of LP spaces. So there are some preliminaries which I'll be assuming, since we have already seen their proofs in either the class or the one of the other presentations. So the first preliminary I'll be using is Holder's inequality. So which states that if P and Q are real numbers, or real numbers greater than or equal to 1, such satisfying 1 by P plus 1 by Q is equal to 1. In some sense, P and Q are conjugates. And if F is in LP and G is in LQ, then FG is in L1. And the first norm, one norm of FG is less than or equal to the pth norm of F into the qth norm of G. So this is the Holder's inequality. And another inequality which we'll be assuming is the so-called Minkowski's inequality, which states that if P is a real number greater than or equal to 1 and F and G are both in LP, then F plus G is also in LP, and norm of F plus G is less than or equal to norm F plus norm G. So both of the proofs for both of these inequalities we have seen in Orko's presentation. So I'll be assuming this. And coming to two other theorems whose proof we have seen in the class. So the first thing is monotone convergence theorem, which states that if Fn is a sequence of non-negative, non-decreasing measurable functions on X, such that limit n tends to infinity, Fn is equal to X for Fn of X is equal to F of X, then we say that we can conclude that F is also measurable, and the limit of the integral is the integral of F. And so this is monotone convergence theorem. And finally, the Lebesgue dominated convergence theorem, which states that if Fn is a sequence of complex measurable functions, by which I mean complex valued measurable functions on X, such that F is once again the pointwise limit of Fn, and it exists for each X. And if in some sense each Fn of X is bounded by a function G in L1, then we can come to the following conclusions, which is F is in L1, limit n tends to infinity, norm Fn minus F is 0, and B of course implies C, saying limit n tends to infinity, integral Fn is equal to integral F. So these are four things which we will be assuming throughout. So now comes the meat of the argument, which is to prove that LP is in fact a Banach space. So as we saw earlier, to prove something is a Banach space, we need to see three aspects of it. One is to prove that it is in fact a vector space, and then we have to define a norm on it and show that it is in fact a norm, and finally give an argument for its completion. So let's just take it piece by piece. So the simplest one, most naturally, is to prove that LP is a vector space. So it's more or less clear that for any C in complex numbers. Oh, I made a typo here. It should have been the math BFC. CF is also an LP because it satisfies both the conditions defining it for any 1 less than or equal to P less than or equal to infinity. And to show closure, we divide it into two subcases. So if we take a P which is finite and greater than or equal to 1, since the function T goes to T to the P is convex, we have, if we take norm of F of X plus G of X to the P, by which I mean complex numbers, this thing is less than or equal to twice the max of norm of F and norm of G whole raised to P, and taking 2 out, and a simple inequality will show that F of X plus G of X whole to the P is less than or equal to 2 to the P times F of X power P plus G of X power P. And so this proves the boundedness condition which we require. So finally, moving on to the case when P is equal to infinity. So let's just expand out the definitions. So what it means is if we have norm F of X is less than or equal to some constant M1 for every X in the complement of a null set, which we call A1, and norm G of X is less than or equal to M2 for every X in the complement of another null set, which we call A2, then by a simple triangle inequality, we can say that norm F plus G of X is less than or equal to norm F plus norm G, which is of course less than or equal to M1 plus M2, which we have now called it M. And this inequality holds for every X in the complement of A1 union A2. But since A1 and A2 are null sets, so is their finite union. So we are done. So all in all, we have proved that so far LP is indeed a vector space. So the next objective is to prove that the norm which we have defined on LP in fact is a norm. So
Nice.
Yeah, I don't.
Can I continue, sir? Can you hear me?
Yeah. Maybe the problem is with my internet or your internet. I think it's from with my internet. I think I don't know. Yeah, my.
Oh, okay.
Yeah.
Can you hear me now? Or?
Yeah, I can hear you now, but suddenly it
Okay. Okay.
the connection got cut. Anyway, now
Abhiram, did you face the same issue or?
No, sir, you got disconnected
okay, I got disconnected.
a while ago now.
Okay. Anyway, it's recording. It's automatically recording. It's continuing. It's okay. You continue.
Okay. So I'll just start from the faithfulness property for p is equal to infinity all over again. So yeah, so the objective was to prove that if norm f infinity is equal to 0, if and only if f is equal to 0 almost everywhere. So that more or less is clear because just by expanding out the definitions, we get this. And so the next objective is to prove scalar multiplication. So let C be any complex number. And by definition, the norm of CF, the infinity norm of CF, is the infimum of every positive m such that norm CF is less than or equal to m for every x in the complement of some null set A. And since this defines a norm on complex numbers, we can pull out the C, and the same statement still continues to hold. And we can just pull out C from the entirety of this definition of this set. Yeah, we can pull it out, and what remains is just the norm, infinity's norm of f. So all in all, we have proved that norm C, the infinity norm of CF is norm C times the infinity norm of f. So the scalar multiplication property has been proven. And finally, we head to prove the triangle inequality. So for triangle inequality, let's just take two different functions, f and g, which are in L infinity. So by definition, the infinite norm of f is the infimum over every positive m1 such that norm f of x is less than or equal to m1 for every x in the complement of some null set, which we call a1, and similarly for the function g, right? And so now by the property of infimum, we get this line. Infimum of by this property of infimum, we get the second line. And by the triangle inequality for complex, the norm of complex same as the norm of f plus g infinity. And once again, since a1 and a2 are null sets, so is a1 union a2, and hence we're done. So we have proved all three properties, which is faithfulness, scalar multiplication, and triangle inequality, which ensures that norm is the norm which we defined is indeed a norm for every case when p is both finite or infinite. And so now we finally come to what we call the major part of the theorem, which is to show the completeness of LP. So let's get into that. So once again, we'll be dividing it into two different cases. So let's take one less than or equal to p less than infinity as the first case and attack it first. So okay, so let's take a sequence fn in LP such that the summation n is equal to 1 to infinity norm fn of p is finite. And we'll show that there exists a function f in LP such that summation n is equal to 1 to infinity fn of x is equal to f of x almost everywhere. So let define two functions gn and g from x, which takes positive values, such that gn of x is just the partial sums of the norm of fk of x, and g of x is just the absolute partial sum, absolute sum. So note that gn is in fact an LP because it is a finite sum. And by monotone convergence theorem, since gn increases pointwise to g, and so we can claim that gnp also increases pointwise to gp, we have that g and both gp are measurable, and this conclusion holds. That is, integral gp d mu is the limit as n tends to infinity integral gnp d mu. And so now, by the hypothesis we had here, that is the summation n is equal to 1 to infinity norm fn is finite. So let's just call that quantity m. And by applying Minkowski's inequality, which is just essentially triangle inequality for this space, we get norm gn of p is less than or equal to summation k is equal to 1 to n norm fk of p. And since this is a sequence of non-negative terms, this is also bounded above by m. So sorry. Yeah. So this g is also in LP of m with norm gp less than or equal to m. So now note that G is finite pointwise almost everywhere. And as summation n is equal to 1 to infinity Fn of x is absolutely convergent pointwise almost everywhere. And we'll now use the fact that C is complete. So it converges pointwise almost everywhere to some function f in LP of x. And this function is in LP because G is in LP and G is less than or equal to f. That relation holds. And furthermore, we have norm f of x is less than or equal to G of x almost everywhere by a simple application of triangle inequality. So now it remains to show that it in fact converges to f, that is Fn in fact does converge to f. Sorry, my mouse is giving me troubles. Yeah, sorry. So let's f minus summation k is equal to 1 to n fk to the p d mu is equal to 0. So essentially what we have proved is that summation k is equal to 1 to infinity fk converges to f almost everywhere, taking the LP now. So what we have done is that we've started out with a series which converges absolutely, and have proved that the series in fact is an element of LP. And by the characterization of completeness which we saw in the class, we are done. So this is the case to prove that for a finite P, LP is complete. So the next objective is to prove that for even when P is equal to infinity, the LP space is complete. And this is more or less an easier case. We just expand out the definition of completeness, which is every Cauchy sequence has. So let's just do that. So let Fn be a Cauchy sequence in L infinity. So so this is endowed with, remember, the supremum norm. So for any given m, a natural number m, we can find a natural number eta such that for j and k greater than or equal to eta, norm fj of x minus fk of x is less than 1 by m for every x in the complement of a null set. So which let's call that null set to be njkm, and we define n to be this union of j, k, m in natural numbers such that j and k are greater than or equal to this eta corresponding to that particular value of m of these sets n, j, k, m. And now since n cube is countable, or n cross n is countable, n is also a set of measure 0. So now note that for every x in n complement, the set fk of x, k belongs to n, is also a Cauchy sequence, which is in complex numbers. But we know that C is complete. So we can define a function f from, I think this should have been n to c. Sorry about the typo again. This should have been f from n to c by f of x is equal to limit k tends to infinity fk of x for every x in the complement of the huge null set which we have got. And so clearly f is well defined, positive almost everywhere, and is measurable. And so now we just let k go to infinity in this equation star, which is the definition of Cauchy sequence. And for each m in natural numbers, we can find an eta such that for every j greater than or equal to eta, fj minus f is less than or equal to 1 by m. And that just translates to this thing being less than or equal to 1 by m for every x in the complement of some null set. So all we have proved is that f is essentially bounded. And so all we have done is that to prove that in fact every Cauchy sequence converges. And this precisely is the definition of what completeness is, and hence we have done. So we have come. So all in all, we have proved that the entire the LP space for any finite or infinite value of p greater than or equal to 1 is complete. So next we look at one interesting theorem. Yeah. So let f be a function in L infinity, whose support is of finite measure. We always assume an underlying measure and a sigma algebra under measure space here. So then f is an LP for every 1 less than or equal to p less than infinity. And the limit as p tends to infinity norm fp is norm f infinity. So this in some sense justifies the notation why L infinity is used.
Again, gone.
Now? Oh, sir. Okay.
Continue.
I'm sorry, my connection was lost, and I hope it's recorded everything. Anyway, I'm back. I'm sorry about
I'll
it.
just send you the slides later. Maybe that's
Yeah, yeah. No, the slides are there.
Yeah, that's. I'll just send you the
Recorded.
slides. Yeah. Okay. So yeah. So our objective was to prove that a limit as p tends to infinity, norm fp is f infinity.
Yeah.
So so we already saw that lim sup of p tends to infinity of fp is less than or equal to f infinity. And now it remains to show that the other direction, which is the lim inf of fp is greater than or equal to f infinity, and we would be done. And that is also more or less a simple epsilon delta positive real number. Then so just consider this set, that is a set of all x in x, such that the norm of the complex norm of f of x is greater than or equal to norm f infinity minus epsilon. And this most definitely must have a positive measure, because if not, f infinity minus epsilon would have been the new f infinity. So let this set have a measure at least a delta. So then from here it's easy to see that the integral over all of x of norm f p d mu is at least delta times what we have here. At least that is at least delta times of norm f. Conclude that lim inf of p tends to infinity, norm fp is greater than or equal to f infinity. So taking a step back, so we've proved that lim sup of fp is less than or equal to f infinity, and lim inf of fp is greater than or equal to f infinity. So it must be the case that the pth norm and the infinite, the limit as p tends to infinity of the pth norm is the infinite norm. So this concludes the proof of this theorem. And finally, one last application of one last interesting theorem about LP spaces. Uh, so let's take P, R, and Q, which are ordered in that fashion, all three finite, such that F is in both LP as well as in LQ. Then we claim that F is in LR for every R in between P and Q. And we have this some property about this, but we will see a nicer form of this property in the proof. So just taking the reciprocal of what we have in the hypothesis, we have 1 by q less than 1 by r less than 1 by p. And so by linearity or any other way, we can say that we have some lambda between 0 and 1, such that 1 by r is, in fact divides, in fact, or I can word it as r divides p and q in the ratio lambda is to 1 or something like that. So so in fact, the point is we can find such a lambda. And solving this linear equation for lambda, we get an expression of the form 1 by r minus 1 by q by 1 by p minus 1 by q. This is that ugly notation which we had up here. And 1 minus lambda is what we had up here. And one interesting point to note here is that 1 by p of 1 divided by p by r by lambda plus 1 by q by r into 1 minus lambda is equal to 1. In some sense, these two are Holder's conjugates of each other. And so this gives a reason to apply Holder's inequality. And so if on applying Holder's inequality, what we get is that the rth norm of f is we'll just write it as lambda plus 1 minus lambda. and taking power r and 1 by r throughout. And next, with the split the norm, we get this thing is by Holder's inequality, we get this is less than or equal to norm of the p by r lambda, the norm of f to the r lambda, and the q by r into 1 minus lambda norm of r into 1 minus lambda whole to the 1 by r. So another typo here, it should be 1 minus lambda, not 1 is equal to lambda. And this is just the pth norm of f whole to the r lambda into the qth norm of f whole to the r into 1 minus lambda, and the whole power 1 by r stays put, and distributing the whole to the 1 by r, we get this. But our assumption was that f is both in LP and LQ, and so these two are finite. So we have proved that f is in fact in LR. And now just taking a logarithm throughout and just writing out the definition of lambda, we get the second statement what we had wanted to prove. So this concludes the section about LP spaces. And next we move on to Banach space. Next we move on to B of S. So let's just define what B of S is. So let S be any set. We call B of S to be the set of all functions from S to C, complex numbers, such that F is bounded. And on B of S, we define the supremum norm, which is the supremum over every S in S of mod F of S. This mod once again is taken over in complex numbers. And the claim is that B of S is also a Banach space. So firstly, let's just prove that it's a vector space, and this is more or less very easy. Or okay, sum of two bounded.
It's same as cell infinity, no? It's easier than L.
Yes, sir.
So you can skip that.
Okay, so let's just prove the completeness of this, and we will be done.
Yeah, that's what it is.
Yeah. Okay, so we'll just prove the completeness of B of S. So let's just take a Cauchy sequence Fn in B of S. So given epsilon, there exists eta such that for every S, by definition, this is what holds. That is norm Fn minus Fn. Infinity norm is less than epsilon. And by the definition of this, we have the complex norm of Fn of S minus Fm of S is less than epsilon for every S in S. And so from here, we can say that Fn of S is a Cauchy sequence in C, and as C is complete, we can define f of x to be the limit as n tends to infinity Fn of x. And so as Fn is, so every Cauchy sequence is bounded. So there exists some positive real number m such that for every S in S, Fn of S is less than f, the infiniteth norm of Fn, which is obviously less than or equal to m. And so finally, letting n tend to infinity, we get that the norm of f of s, which was in fact the limit as n tends to infinity norm f of s, is also less than or equal to m. So the function f, which we had defined using the completeness property of C, is in fact a bounded function. And it now remains to show that this is where Fn converges to. And that is also more or less clear because for every S and N, since the norm is a continuous function, taking the limit as m tends to infinity, the inequality which is less than epsilon still remains true. And so we've seen that for every n greater than or equal to eta, norm Fn minus f is less than epsilon. So hence we can show that sequence Fn is convergent to f. So we started off with the Cauchy sequence and proved that it is convergent. So finally, we've proved the convergence of the completeness of B of S as well. So this ends my presentation. So just some references which I have used. And finally, one more shout out to Abhiram for reading through the entire manuscript in extreme detail and suggesting some very helpful corrections. So thank you.
Okay, good. I mean, I made a mistake. I mean, my mobile hotspot was on, so it got connected to that. That's why the disturbance was. Later, this recorded well. So I hope Zoom recorded the whole thing. Okay.
Okay.
So yeah, so it's good. So let's meet tomorrow then.
Okay, sir. Thank you, sir. Thank you for the opportunity once again.
Yeah. Thank you. Bye.
Bye, sir.